Hello and welcome to this video where we will be continuing our journey into quantum gate logics. What we have seen in the previous video is the notation of how we can interpret or demonstrate the logic of the circuit in terms of the Dirac notation, where we have learned about the bracket notation, the operations over it, how the base state and its amplitude in terms of calculating the probabilities are represented in Dirac notation. What we're going to do now is to look into the first quantum circuit on the basis of what we have learned in the previous video. So a quick refresher, what we have seen in the last video is about qubits, where we demonstrated that qubits are nothing more than superpositions of quantum bits or the states that those bit represents. Just like in classical computing, where a bit has a state of 0 and 1, a quantum state can also have a discrete basis state, which are typically labeled in the Dirac notation as zeros and one, and they represents column vectors. Qubit then is nothing more than superposition of this base state with their respective amplitude. And it is good to know that the amplitude, for example, alpha and beta, what has been represented here, belongs to complex number. However, the basic principle that we have also spoken about earlier is that when the amplitude square of the various states are added, they should add up to 1. So alpha square plus beta square should add up to 1. However, it is important to note that once a qubit is measured, once the state has been measured, then the alpha square or the beta square represents the probability of whether to find the measured state in either 0 or 1, so which has more probability, and therefore the measurement collapses the superposition state of the quantum. Now, what is at the core of quantum computing in terms of what we have discussed so far? And this is about changing the amplitude of the qubit to which different states may carry at different point of time. And this is the crux that the logic gated operation, just like in the classical computing where you have the gate operation, in case of quantum computing, the quantum gates are being applied to alter what you called as the amplitudes or the probability, which is amplitude squares of a qubit. Now, to help you visualize this better, we can look at the most classical representation of qubit, which is called as a blockosphere. And just for the brevity and the simplicity, we are at this point of time only considering real number as amplitude, not complex, and that is to keep the discussion simple. So a block sphere is nothing but a unit circle depicting the state of the qubit. So for example, as you can see, the first state where the qubit is pointing to is a 0 state. That's why the arrow is pointing to the right and ending on the right on the circumference of the circle. But it could also be that it is pointing upwards and then it is representing the state 1, again stopping at the circumference of the circle. It is also possible that the state lies in between in the orthogonal state of zeros and ones somewhere on the circumference of the circle, as you can see in the third representation. Here, the point to be noted is that even though the amplitude looks different, if you square and add them up, they will end up to 1, maintaining that the positioning of the state on the circumference of the Bloch sphere. You can also apply what's called as a phase shift, where negative amplitude can represents the value. However, if you do apply the square operation over it, you will end up finding it that it is still adds up to 1. So there are various ways of representing the qubit on a Bloch sphere. This is easier for the visualization perspective. It is also important to note that what you call as degeneracy, that a multiple quantum state account for probably same probability distribution. And what we see here is the arrows with different color, having different amplitude, representing probably different states of a qubit. However, if you now take the probabilities of finding the base state of zeros and one, square them and add up to them, they all will add up to 1. So this is a unique thing in quantum where the multiple states can have the same probability distribution, and they mathematically end up representing the same thing. However, it is also to be noted that each state might interfere differently with the same operation. For example, the gates, that is what we apply to achieve operations on qubit, and that is where the amplitude and the core of quantum computing to manipulate that amplitude comes into the picture. To give you a glimpse of how it is to consider Bloch sphere with complex number, here you will see that the representation is a bit more complex than what we have seen in the previous slides. And if you particularly, for example, focus on amplitudes which are having a complex representation in them, for example, on the Bloch sphere, on the plane of the Bloch sphere, you will see that the phase shift is now being represented a bit differently. However, the basic principle, as I said before, of squaring the amplitude and adding up should still result in 1. So this is with the complex number, it is a bit of a difficult representation. However, this gives you more clarity in terms of where actually in the vector space you end up seeing a qubit, and what probability of a particular state happening can also be very easily visualized. So I'll stop here. Thank you very much for watching, and I hope to see you in the next video.